So here we have part 2, and here we will see multiple pumping wells, confined aquifers, and this is the main equation for confined aquifers. So for one well, this is what we have, and then for multiple wells, what you have is this term here that you have to add for each flow rate and each distance from the observation well and the actual well. So maybe it's better explained with an example. Here we have 2 discharge wells, 1 and 2, penetrating a confined aquifer that are pumped at constant rates of 3140 cubic meters per day. So here's well A, 3140 cubic meters per day, and then well B, which is 942 cubic meters per day. The coefficient, or the aquifer transmissivity, is 1,000 square meters per day, and the steady state drawdown measured at an observation well is 1.2 meters, and this observation well is 60 meters from well 1 and 100 meters from well 2. You need to determine the drawdown of another point in the aquifer that's located 200 feet from well 1 and 500 feet from well 2. So as you can see in this case, it's extremely important that you have a drawing and a sketch to make sure you understand what's going on. So we have the drawdown at an observation well, and we know information about well 1 and 2, or A and B, and this is the drawdown that we want to predict. So of course this is the expression. So we have 2 wells, and this is the drawdown from that observation well. So we just substitute appropriately. So let's take a look at the substitution. So this is the drawdown from that observation well, and this observation well is 60 meters from well 1 and 100 meters from well 2. So if we look at well 1, what we need to look is the 60 meters and the 200 meters. So well 1 is 60 meters from the observation well that has the 1.2 meters drawdown, and then 200 meters from another observation well that we don't know the drawdown. Okay, so this is 60 and 200, and this is my well. So now I look at well 2, and in well 2 I am 100 meters from this observation well that I know the drawdown, and 500 meters from the one that I'm looking for the drawdown. So here's the 100 and 500, and of course the flow rate. So I just do the appropriate substitutions, and I have the 0.357 meters. Okay. Now let's look at unconfined aquifers. I find this more fun, and remember we have very similar notation, except we don't have the thickness of the aquifer. We have here the HO and RO, so here's like the radius of influence, and at a diameter or a radius equal to that or larger, you will have this HO, no drawdown. Okay? So if you have the radius from the well, then this is the drawdown at that distance from the middle. So here's the drawdown at any other distance R. So this would be the drawdown at any distance. So remember, the drawdown would be H naught minus H. Okay? So we have in unconfined aquifers a steady radial flow. Water table equals the piezometric surface. The drawdown is the change in piezometric surface, and the cone of depression is axisymmetric drawdown that forms a conic geometry. So it's like a cone. The area of influence of the well is the outer limit of the cone of depression. So these are the expressions also derived from Darcy's equation. But in this case, when we integrate, it's important that you recognize here is HOB, okay, and this is ROB, which is an observation well, for example, that you know which is the depth and the drawdown and or the drawdown. And then this is W, which is the radius of the well. So let's look at an example. I have a 95 feet thick unconfined aquifer that is penetrated by an 8-inch diameter well that pumps at a rate of 50 gallons per minute. And the drawdown at the well is 30.5 feet and the radius of influence is 500 feet. Determine the drawdown 80 feet from the well. This is kind of a two-part problem where now we'll see how to calculate K for an unconfined aquifer. So remember, we were looking at different ways of calculating that coefficient of hydraulic conductivity, and so this is the third method by field experiments. So the first thing is to make sure you have all the units correctly. So we need cubic feet per second, so the 50 gallons per minute converted to cubic feet per second. Here is the drawdown at the radius of the well. So I have that information, which is the H naught, which is 95 feet thick, okay? And it tells me the drawdown at the well, which is 3.5 feet. So it's giving me this information here, 3.5 feet. And so the HW would be this 91.5 feet. If you look at the equation, and that's why it's so important to always write the equation, is that for this first part, you know everything except the coefficient of permeability, and that's the way we do it. So before we can find the drawdown at any point, we need to have that coefficient of permeability, because otherwise we would have one equation and two unknowns. So we will solve for the coefficient of permeability, and then now, once we have the coefficient of permeability, we can look at the information that is requested, okay? So this would be the coefficient of permeability, and remember, you can pause it. And so what I have done here is just wrote down a summary of the information that is provided so that you can understand how to do the appropriate substitutions. So now, having the coefficient of permeability or the hydraulic conductivity, we can then estimate what's the drawdown 80 feet from the well. And so we have the drawdown at the radius of the well, which was 0.33. And this is the coefficient of permeability that we obtained, okay? And this is what we want to find, the drawdown at 80 feet. And this is the 91.5. Let me go back so you see. This is the 91.5. And then the radius is 0.33, which was 4 inches. So then we can find the H, and of course then the drawdown, which is H naught minus H. Okay. So now you have the same situation of multiple wells for unconfined aquifers, and it can be the same thing. They can overlap or not, but you don't know until you have this equation solved. So here you have the different notation. So look at this notation, which is so important. So you have your A, okay, and reviewing also for confined aquifer. So you have your well A, and then this is RA, which is the distance to the observation well, and then here you have RA naught. So here we have from 0, the observation well, to A. Here you have the distance from B to the observation well, and here you have distance B to Z. And you can use different notations, but let's take a look at this problem. So what I've done is the same things where you have the main equation and then you have to find what is what here. Okay? So you have two discharge wells, 1 and 2, penetrating an unconfined aquifer that are pumped at constant rates of 3,500. So you have 3,500. The steady state head measured at an observation well is 40 meters. And this observation well is located 50 meters from well 1 and 64 meters from well 2. The water table measured at the second observation well is 32.9, and this well is located at a distance of 20 meters from well 1 and 23 meters from well 2. So here you have your information. I apologize. Let me look here. So here is those distances, and then of course you have your 50 and your 20. And I apologize, kind of went back to a different monitor. So you have 50 over 20 and 64 over 23. So you have your 50 over 20, which is for my well A, the distance from the two observation wells, and then for B, I have the 64 over 23, which is the two distances, and then I can obtain the coefficient of permeability. So really this completes the introduction to wells. We'll be doing more problems in the classroom, so thank you very much.